Okay, right. Hi everyone. Hopefully this is all working and you can hear me fine, otherwise I have to re-record. Yeah, hopefully by now you know my name. I'm Ollie, and I'm basically just making this video as a sort of stats refresher or introduction for any of my students who I'm going to be supervising. Um, Basically because some of you might have been away from stats for a while, or this might be your first time dealing with stats, and there's a lot to sort of juggle before you get to the point of actually analyzing your data. So wanted to make sure you have a bit of a refresher before you start, just so you can make the best decisions for your study as we go. So we're going to do a bit of the basics, get the sort of reasons why we like statistics out of the way early, and then we'll look at sort of actual analyses and options that you have down the line. For the visualizations, we've recently moved towards Jamovi. So most of the visualizations will actually be dealt with within Jamovi, and you won't have to do anything additional, which is nice. But just in case further down the line, I'm going to make some resources for RStudio, which gives a bit more customization, but isn't necessary. So hopefully this doesn't need stressing too much, but just in case you are new to psychology, data is super important to us. We're a scientific discipline, which means we look at research, we make hypotheses which are testable, and in order for them to be testable, you have to have a specific analysis in mind. Okay, it's no use me saying that intervention X will do Y if I don't have a proper way of assessing whether it has achieved that. So that's really why we have data and analysis at the sort of core of psychology. It allows us to be more objective, and also our current approach is to improve transparency. So a lot of the open science stuff that you may or may not have heard about is about making data available online, pre-registering our studies so that we're very upfront about what we expect to find, and so that we're not just sort of exploring results and saying, oh, look what we found. Instead, it's a properly thought out ahead of time. So first things first, we need to understand the different types of data available to us. So there are three categories that this falls into. The first one is categorical, or sometimes referred to as nominal data. This is data that is kind of like it says on the tin. It's based on categories. So if you think of crisp flavors is one of the sort of examples we often use. We can split people into their favorite crisp flavor, and those groups have no numerical value, right? If someone picks ready sorted, we might call that group 1, but that group 1 doesn't have any numerical meaning. It's just what we call arbitrary. Okay, so any sort of condition or group or classification that doesn't have numerical meaning is a categorical data. So if we use the example of a clinical trial, we have the drug that may or may not be used, and so that forms the intervention condition and the control condition. It doesn't matter if we call one of these group 1 and the other one group 2. We could swap those around and it wouldn't matter because they don't have numerical meaning. So that's categorical data. We then have ordinal, and this is where it gets a little bit trickier to differentiate. So if you've ever completed a study for someone else, you will very likely have seen the use of Likert scales. This is where you're asked to respond basically on a 1 to 5 scale, or sometimes it's 1 to 7 or more, but the classic is 1 to 5. Now, this becomes tricky to differentiate from continuous data, but there is an important difference. With ordinal data, those responses are essentially ranked. Okay, so if I'm asked how extroverted I am, and it's on a 1 to 5 scale, I only have 5 options, firstly. But secondly, I could pick first, or the most extroverted, the second most extroverted, or so on. Whereas in continuous data, these scores are a little bit more natural and they can fall anywhere within that range. So classic examples are things like response time in like milliseconds, or height in centimeters, or even the amount of errors made. Okay, you're not restricted to a sort of subset of responses. And another thing that's really important to think about here is whether or not you can assume there are equal differences. Okay, and what I mean by this is if you imagine a race and you've got the front three, they all come through the finish line at different times. You get first, second, and third place. Now, on the face of it, they're all one position apart from one another. But in reality, we have no idea how close or how far apart they were. First and second might have been neck and neck, and then third, a whole minute behind. But ordinal data only captures first, second, third. Continuous data, on the other hand, would be time in this instance. And so you would see the person who came in first was 1 minute and 32 seconds, or whatever it might be. And that the person in second was 1 second behind. So continuous data is really telling. It tells us a lot about the actual world, whereas ordinal data is a little bit more structured, but that's not to say it's bad. In fact, ordinal data is often how we collect data in psychology. A lot of our scales are based on these Likert scales that I talked about before. And that's why there's no right or wrong type of data, but you just need to understand that they are different and that they must be handled and analyzed in appropriate ways. So I've included how some data might look. I imagine most of you are probably familiar with this. This is Jamovi. And so just thought to have a quick look at how categorical, ordinal, and continuous data might look in Jamovi or an Excel spreadsheet. So first of all, we have gender and ethnicity here. These are categorical variables. And the reason being that, let's go with gender, for example. We might have male, female, non-binary. Now I could label male as 1, 2, or 3. It really doesn't make a difference to the analyses that we're going to do, because that number would be arbitrarily assigned. Okay, so it's just really important to understand that the number we give them doesn't make a difference. And in Jamovi, it actually has a very nice feature that allows us to very easily convert these into their sort of original names. So if you click the actual gender tab header there, you get this little section come up. And here you can see that the measure type is set to nominal. That's the same as categorical. And just to the right of that, you have levels. Now, originally, these were called 1, 2, and 3. And here I've just put in the names of these variables. In the subsection of data that I have, we only had male and female. So female was coded as 1. So I type female in the first box and then male in the second. Now, the first few rows here are ordinal data. These were collected from a depression questionnaire where participants are asked to respond on a 0 to 4 scale, or 1 to 4 scale, sorry. And so let's say the first one here, dep_5, was I feel restless or tired. And then participants were asked to respond whether that's very rare or, on the high end, very common. Okay, that's ordinal because it ranks data with sort of select responses available. You can't put 3.5, for instance. On the other end, however, we have cognitive errors, and this is logged as continuous data. And that's because there isn't a sort of set choice available to the participant. However many errors they made is logged. If we were to turn this into something ordinal, we could, at the end, ask them how many errors they made, they think they made, and allow them to score it on a scale of 1 to 5, and that would then change this into a subjective but ordinal data instead. Okay, so in your data sets, this is something you need to be aware of, but hopefully as you go through these things, it all starts clicking and making sense. So let's think about what analysis options are available to you. Now, in psychology, broadly speaking, we're looking at one of two things at a given moment. The first of these is looking at differences, and the second is looking at relationships. Okay, so in the differences section, we're thinking we have some sort of groups. The example I've used here is a clinical trial. So we have the experimental trial and we have the control trial. And we're seeing if there is a difference in outcome, maybe depression, between these two groups. So our test here is focused on the differences between these groups. On the other hand, relationships are focused on association. So we take two continuous variables and we see how strongly they relate to one another. Okay, so the important thing here is if you have a categorical variable, for the most part, you will need to be looking at some sort of difference. Okay, now there are ways to do things like regression with categorical variables, but that's in psychology is quite rare and not something you really need to worry about unless you go down a very specific route. Okay, whereas for most of what we do, when we look at relationships and regression techniques, that's going to be with continuous variables. So let's look a little bit deeper at differences. Now, whenever we have just one factor, so like in the example before, we had clinical trial where you either got the drug or you didn't, you were in the control group. Here, you'll be doing some sort of t-test, okay? And we can do a couple different things with t-tests. The first is an independent t-test, and this is where we have two different sets of participants who are sort of unmatched, they're sort of randomly collected, and we just want to see if they have different scores in the dependent variable. So this is just like the clinical trial I explained before. So group 1 might have this score for depression, group 2 might have this score. We're seeing if that's significantly different. The one sample t-test is a little bit like this, but it's where you only have one group of participants. So maybe you don't have access to that second group. As an example, maybe in a clinical trial, it's not ethical to not give some people the treatment. So you might have to do a one sample t-test. And here, most of the time, we compare our group score to 0 and see if it's significantly different from 0. You can set specific values if the value you need to know is known. So what I mean by this is if we look at IQ, the average IQ is 100. So if you wanted to see if our one group was higher or lower than that, you could use a one sample t-test with your value set to 100, and you can see if it's significantly different from this value or not. And then the final option is a paired samples t-test. Okay, so we have a couple of options here. The first is to use the same participants twice. Okay, so imagine we're doing a clinical trial again, but this time we have to give everyone the drug. We can measure their depression at time 1 and then measure it at time 2 after the intervention. Because those two groups are the same participants, this counts as a paired sample. Now, if we wanted to stick to our original design where we had different groups, what we'd have to do is match them in some way. So let's say I'm sat in my lecture and I want to see if revision effort is related to exam performance. I could just split everyone right down the middle of the lecture hall. However, what if by some chance everyone who sat on the right side of the lecture hall was already doing better? They were already all getting firsts, whereas everyone on the other side were all getting lower grades. then my two groups wouldn't be equal, and so it wouldn't be a representative test. So what we could do instead is match participants to one another. So I could take someone from random, and they might have an average of 68 on their grades. I then take another person who has an average of 68 and put them in group 2. I then do that the whole way down so that every participant I recruit in my first group has an equal grade to those in the second group. And that way we match them on this sort of confounding variable. Now, this is very rare. I've certainly never had to do it, but it's worth thinking about, just in case there is a really strong chance of you get one of these confounding variables. But most of the time when we see paired samples, it's because we've used the exact same participants twice, but at another time. So independent t-tests are, for the large part, the most common that I see. And this is where we have one categorical variable. So clinical trial example, we have condition 1 and we have the control. And then our dependent variable is something continuous, i.e. depression. Your data will probably look something like this. So in one row, we get the categorical variable, and in the next, we get the depression score. Now, this might look slightly different if we're instead doing a paired samples t-test. Okay, imagine we're going for the example where we have the same participants, but at time 1 and time 2. And there was some revision intervention in the middle of these 2 times. Here, we expect our data to have one row identifying the participant, one row with their grades from time 1, and then another row with their grades from time 2. And these grades should be something continuous. So here I've done a score out of 100. Okay, so that's t-test. Now, for anyone doing their masters, you probably want to be doing something more than a t-test, so something a little bit more complex. Many FYP students will also end up doing something a bit more complex. But even these more complex analyses might end up with you doing some sort of t-test as post-hoc comparisons. So it's important to know what they're doing. So we can complicate these matters in a couple of ways. One way is to expand the number of levels that we have in our categorical variable. So if we go back quickly to our independent t-test, here we've got one categorical variable, but 2 levels, either condition 1 or the control group. In a one-way ANOVA, we can have more levels, but still with only one categorical variable. So here we still have our condition, but people are either in drug A, drug B, placebo, or control. Okay, so that's 4 levels. So a t-test wouldn't be able to handle that many levels, and that's why we have to upgrade to a one-way ANOVA. And this allows us to look at data like this. Essentially, we've got one factor here, and that's whether you're in drug A, drug B, placebo, or control. And then the dependent variable is, in this case, well-being. Now, we can complicate matters even further and have multiple factors or categorical variables. So here, I've got the same data as before, but in this instance, I've also measured gender. So I want to see if gender and condition have an effect on well-being. And so this would be a 4x3 between subjects design. Why is that? Well, in our first variable, condition, we have 4 options or 4 levels. In our next one, we have 3, because I've measured female, male, and non-binary. And all of these participants would only complete this trial once. So therefore, it's between subjects. Equally, if we kept just one varying condition, but wanted to measure before the intervention and after, then we'd get something that looks like this, where we've still got our same condition row, but now we have 2 rows for our outcome, one for time 1 and another one for time 2. And that should say 4x2 mixed subjects design, my apologies. The reason it's 2 is because we have 2 time points. So we've got 4 different conditions, and then time 1 and time 2. So that's ANOVA. And if you are thinking of doing an ANOVA, I'm going to have a separate video, which will be a tutorial just for ANOVAs. But in essence, you'll run the ANOVA, you'll see if it's significant, and then if it is significant, you can do what's referred to as post hoc comparisons, which is essentially looking for where specifically your significant effects have come from. So if instead you're not looking at differences and you're looking more for associations, relationships, then you'll be using some sort of regression technique. Now, at the simplest level here, we have bivariate correlations. And this is, put simply, you take one continuous variable, another continuous variable, and you see whether or not they go up together. So here I've got the example of height and weight. Now, this isn't a perfect relationship, but it's a pretty strong positive relationship, meaning that as height goes up, typically so does weight. Okay, other examples are things like temperature and ice cream sales. Right? As it gets hotter, ice cream sales tend to go up. You can also get negative associations. So as stats anxiety goes up, exam performance goes down. And that can still be a strong relationship, but it will be a negative one. And these sorts of correlations are what all further, more advanced regression techniques are based on. So kind of like t-tests, we wouldn't expect many people to rely solely on correlations, but it's a good starting point. So one step up from correlation, we have simple regression. Now, the data will look pretty much the same, but it's a different hypothesis and a sort of different set of assumptions. So your output will be different, but the core data will be the same. And here you're essentially asking, how strongly does X predict Y? So one of the key differences here is that you don't just have 2 random variables that you're sort of seeing how they associate. Instead, you're saying X predicts Y. So you have a sort of difference here between the predictor and the outcome. Now, I wouldn't expect many people to look at just simple regression either, simply because in the real world, it's very rare that you have just one variable that perfectly predicts Y. So most of the time, it makes sense to include some other variables. And we do that by looking at multiple regression. Okay, thinking about the exam performance variable, we might have things like revision effort that go into predicting exam performance, but there might be a whole list. So here I've got things like revision time, coursework grades, attendance, and stats anxiety. Note that they might not all be positive. Stats anxiety might have a negative association with exam performance, but we can test them all in one regression model, as long as we use multiple regression. So this is where the power of multiple regression really comes in. And now there are a few different ways to advance this even further. You can do things like hierarchical regression, but just like I mentioned earlier, I'm going to do further tutorials on these specific techniques down the line. So if you're interested in sort of complicating the regression techniques even further, then go watch that video instead. So one way we can advance these techniques without sticking within multiple regression is by looking at mediation and moderation. And these are the last 2 that I'm going to look at today. So these start with essentially a simple regression, and that's this line between independent variable and dependent variable. Okay. So we might have revision effort and exam performance. Now, a lot of people get confused between mediators and moderators. And it's very understandable. They are looking at similar things, but they are equally very distinct. So a moderator is looking at how the relationship between X and Y will change based on your levels of the moderator. Okay, so that's why we have this arrow sort of intercepting that direct relationship between X and Y. We're saying this will alter that relationship. The mediator, however, is almost like an indirect pathway, right? So we're saying X and Y have this relationship that might be explained by this third variable up here. And so that's why, rather than an arrow that intercepts our XY relationship, we instead have arrows that represent this alternative pathway. So, like I said before, we're going to be looking at revision effort and exam performance to explain these a little bit further. So essentially what this is saying, the harder someone tries to revise, the better their exam performance will be. So let's say we did a study last year just with these two variables, and we found that it was significant. We could do a follow-up this year, trying to essentially explain more about this relationship. So let's start with the moderator, and we think, well, if someone attended all of the lectures, they are going to have a stronger sort of starting point when it comes to revision. They're going to be consolidating information they've already learned rather than learning it for the first time. So maybe we'd be thinking that people with better attendance might display a better relationship between their revision effort and exam performance, essentially because it's easier for them. They've got a better starting point. Whereas people with poorer lecture attendance might need to start learning all these things for the first time. They might have less time to do all of that. And so the relationship between revision effort and exam performance might not be so clear. So we would have started with a relationship that looked like this. As revision effort goes up, so does exam performance. But when we break this up into high, medium, and low lecture attendance, we might see something different. So we might see a nice, strong relationship between these two variables amongst those with high lecture attendance. It might get weaker when we look at those with medium lecture attendance, and it might still be there, but very weak with those with low lecture attendance. And so if you go back to this diagram, what this is saying is that we still have this XY relationship. So revision effort leads to better exam performance. But what we're saying is that for different levels of lecture attendance, this relationship will behave differently. And that's how we end up with something like this. So that's moderation. If we now think about mediation instead, we're thinking about something that explains this relationship. Okay, so we're not saying it alters the relationship, but it offers a sort of another explanation for this causal relationship. So here, I might posit that self-efficacy is actually driving exam performance. So in this relationship, we first saw revision effort leads to better exam performance, but maybe my hypothesis would say revision effort increases self-efficacy. So that's, I revised a bunch of stuff about statistics. I now feel more confident in my ability to handle statistics, and that confidence, self-efficacy, is what will drive my better exam performance. So it's a little bit more of a convoluted path, but it might be more sort of close to the truth. So how we know if it's the mediator or not is based on these three criteria. So first of all, it should be caused by the independent variable. So in this case, we're saying revision effort will increase self-efficacy. That must then influence the dependent variable. So this is true from the literature that we have. Self-efficacy does improve exam performance. So we know that this is sort of fulfilled. And the final thing is a little bit more statistical, but essentially it's that this overall result of the mediation must be stronger than when looking at just the direct relationship. Okay, so let's take our study last year. Revision effort increased exam performance. Let's say that had a simple regression, and it was around 0.7. So a nice, strong, or really strong relationship. But then when we include this mediator and look at the mediation analysis, if this strength of relationship improves, that means that we're learning more about this relationship because we've included self-efficacy, and therefore we've explained more about this relationship. Okay, so that's a little bit about mediation. Just like the others, I'll do a separate tutorial on moderation and mediation. But essentially, if you have a simple or multiple regression that you want to expand in a little bit more of a complicated way, you can look at these two things to add a bit more complexity to that relationship. Okay, so like I said before, separate tutorials will be coming on all of these. If you have any questions, feel free to email me at any time. But yeah, hopefully this video helps to have something to refer back to just as a refresher or introduction. So yeah, thanks for listening, and I'm sure I'll see you all soon. Bye-bye.